Hello my friends and welcome back to the You Can Do TV channel. A circular approach to battery recycling at Clarios, Ho Chi Minh showcases one of Europe's longest-running lead-acid battery recovery operations, active on the same site since 1904. What began as an accumulator factory has evolved into a fully modern, high-efficiency recycling plant processing up to 6 million automotive batteries each year. The facility employs 125 highly skilled workers and operates under strict environmental and safety standards, contributing directly to regional sustainability and the circular economy. Operations start with the arrival of roughly 1,000 end-of-life batteries per hour. A wheel loader feeds them into a heavy-duty breaker, where housings are opened and sulfuric acid is drained, filtered, and stored for external reuse. The de-acidified batteries are then transferred to a preparation area, where iron, battery fractions, and coke are accurately weighed and blended to produce a consistent charge for the shaft furnace. The shaft furnace, running 24/7 at about 100 degrees Celsius, melts the feed mixture to generate high-purity work lead. A continuous front tap delivers molten lead at around 900 degrees Celsius with 98% purity, while slag is periodically tapped on the side, cooled, and mechanically separated into recyclable fractions. Slag portions are reintroduced into the furnace, while sulfur-bearing leadstone is shipped to specialized refiners. Furnace off-gas passes through thermal afterburning and large dust collection filters before clean emissions exit a 100-meter stack. In the refining area, 7 kettles of 100-ton capacity each remelt and upgrade the lead to 99.8% purity, adding elements such as antimony, tin, or calcium to meet customer alloy specifications. A high-capacity casting line produces 50-kilogram ingots at up to 22 tons per hour, with robotic oxide removal, stamping, bundling, and dispatch to Clarios battery plants across Europe. Supporting systems include water recycling loops, rainwater treatment, a dedicated tire wash and site sweeping fleet, robust flood protection, full fire detection and sprinkler networks, redundant emergency power, and continuous laboratory monitoring. With advanced management systems and strong apprenticeship programs, Clarios Ho Chi Minh remains a benchmark for safe, resource-efficient lead-acid battery recycling in Europe. Deep cycle battery manufacturing at US Battery highlights an American producer with nearly a century of expertise and 3 modern plants in Corona, California and Augusta/Evans, Georgia. The process begins with raw lead alloy melting, where controlled metallurgy produces durable double-cast grids. After trimming and aging, the grids harden to form a robust foundation for deep cycle plate structures designed to withstand heavy discharge cycles. A key differentiator is the company's proprietary XC2 diamond plate technology, which optimizes paste conductivity and increases active material utilization. Mixed oxide paste is applied precisely onto the grids and flash-dried before entering curing ovens. This produces stable crystal morphology, giving the plates higher capacity and extended life compared with conventional deep-cycle designs. In assembly, cured plates are hand-stacked with separators to form cell groups. Skilled technicians fabricate and fit lead strap connectors and intermediate terminals to ensure low-resistance current paths. Cell groups are inserted into polypropylene cases and welded using automated equipment. Every battery undergoes high-voltage short-circuit checks and weld integrity testing before heat-sealed covers are applied. Electrolyte filling, formation charging, and topping off create the final electrochemical structure. Batteries are washed, brushed, capacity tested, labeled, and date-coded before palletizing for shipment. Through continuous reinvestment in American manufacturing standards, U.S. Battery delivers deep-cycle products with high initial capacity, long operational life, and consistent performance across golf, solar, marine, and industrial applications. How are batteries made? Begins with Max Hunt's visit to VARTA's Hanover production facility, guided by longtime quality manager Dirk Oldenburg. With more than 3 decades at the plant, Dirk explains VARTA's heritage, tracing its origins to 1898 and the establishment of the Hanover factory in 1938. What once relied on extensive manual work has transformed into a highly automated system capable of producing over 11 million automotive batteries annually. The tour starts with the core raw material lead. VARTA uses 350 to 400 tons of recycled lead per day, contributing to the battery's exceptional recyclability rate of over 98%. After melting, the metal is cast into strips, rolled to 1 mm thickness, and stamped at high speed to form precision grid plates. In parallel, pure lead is atomized and oxidized in sealed systems to produce lead oxide dust, which is pneumatically transferred to the paste mixing units. Here, positive and negative paste are formulated and applied to the grids before being laminated with fiberglass mats. Approximately 4 million plates are produced daily and undergo controlled curing to stabilize their electrochemical structure, one of the most critical steps in battery performance. Assembly integrates separators, cases, lids, and plate groups. Positive plates wrapped in glass fleece are paired with negatives and joined using molten lead strap casting. 6 plate groups are inserted into the 6 cells of each housing, followed by short-circuit testing, cell welding, and lid sealing. After terminal soldering, each unit receives sulfuric acid, initiating the chemical system. Batteries then enter water-cooled formation charging, which may take hours or days depending on the model. Following washing, voltage retention checks, labeling, and ergonomic handle installation, the batteries are packaged for distribution. With VARTA producing 35,000 units per day, the plant demonstrates advanced manufacturing and sustainability, even as electric vehicles continue to rely on robust 12-volt support batteries. A lead-acid battery recycling plant begins with the battery breaking machine, where scrap batteries are hydraulically cut into sections and the released acid is collected for effluent treatment. Crushed battery pieces move by conveyor to the shredder stage, where an intelligent crusher reduces them further using water as a coolant. The slurry then enters the secondary crusher, producing a mixture of plastics, lead, and ferrous metals. Magnetic separation removes ferrous materials, and the remaining fragments are washed. In a water-filled hopper, low-density plastics float for screening, while lead sinks and is conveyed to a shaking table. Here, metallic lead and lead powder separate. Metals go to pot furnaces for melting, while powders are smelted in rotary furnaces. Meanwhile, the effluent treatment system neutralizes and clarifies all acidic wash water through equalization, pH adjustment with lime, coagulation, settling, filtration, and final polishing before reuse in the process. The coal and mineral industry plays a foundational role in the national resource economy, supplying critical raw materials for power generation, metallurgy, cement production, fertilizers, chemicals, and various heavy industrial sectors. Modern mining technologies are deployed across both underground and open-pit operations. In underground mines, fully mechanized longwall systems, automated roadway development equipment, advanced ventilation networks, and real-time gas monitoring ensure stable output while maintaining strict safety standards. Open-pit mines utilize high-capacity excavators, electric or diesel haul trucks, precision drilling and blasting systems, and integrated conveyor transport to optimize overburden removal and reduce operating costs. Beyond extraction, the industry emphasizes deep processing of metallic and non-metallic minerals through a network of smelting and refining facilities for copper, zinc, tin, chromite, and other metals. Large-scale alumina complexes operate with integrated beneficiation, slurry transport, calcination, and residue management systems, establishing a new industrial base for the country. Environmental sustainability is reinforced through closed-loop water treatment, tailings management, dust suppression technologies, and land rehabilitation programs. With stable annual output, increasing mechanization rates, and continuous innovation, the coal and mineral sector remains a strategic pillar, ensuring national energy security while supporting regional economic development and long-term industrial growth. The graphite mining process at Sri Lanka's Ragadara mine, one of the world's purest vein graphite deposits, demonstrates a highly specialized underground extraction method developed over more than a century of operation. The tour begins at the surface infrastructure, where ore samples are logged, ventilation systems monitored, and safety protocols briefed before miners descend through narrow shafts, reaching several hundred meters deep. Inside the mine, workers follow naturally occurring vein structures formed in metamorphic rock. Unlike flake graphite deposits, Sri Lankan vein graphite occurs in concentrated, high-carbon seams that can reach 90 to 99% purity directly from the rock face. Miners drill short blast holes, mechanical chiseling, to expose the vein while minimizing dilution from host rock. The mined graphite lumps are carefully chipped from the vein, then loaded onto small rail carts that transport the material along the underground rail line to the surface. At the processing plant, ore passes through coarse crushing and hand sorting stations, a hallmark of Ragadara's low-impact beneficiation approach. Since the graphite is naturally high-grade, minimal grinding is required. Concentrates are washed, dried, and screened into various size fractions for industrial applications such as battery anodes, lubricants, and thermal management systems. Double robot load and unload on the COS, cast-on strapline, showcases Mac's advanced automation for high-precision battery assembly. In this system, two coordinated industrial robots manage the continuous loading of plate groups into the COS station and the unloading of completed strap cast assemblies. Vision alignment and servo-controlled grippers ensure each plate group is positioned with exact dimensional accuracy before molten lead is cast to form the intercell connection. After cooling, robots remove the finished groups and transfer them to downstream inspection or assembly modules. By eliminating manual handling, Mac's dual robot system increases throughput, improves joint consistency, and enhances overall production reliability for modern battery manufacturing. Enerocket's manufacturing complex in Ho Chi Minh City operates as a fully integrated VRLA production hub, engineered around precision plate fabrication, controlled curing, and automated assembly. The process begins with virgin lead melting and alloying, followed by grid casting on temperature-regulated continuous machines to ensure uniform thickness and metallurgical stability. These grids move to automated pasting systems, where oxide paste is applied under strict control of moisture content, density, and plate mass. Pasted plates enter 20 climate-programmed curing chambers, where humidity and thermal cycles drive active material crystallization essential for long service life. After curing, positive and negative plates are wrapped with high-porosity AGM separators, designed to maintain ionic pathways and prevent dryout during deep cycle operation. Cell packs are inserted into molded ABS cases, then advanced through sealing, terminal welding, O-ring insertion, epoxy isolation, and leak testing using differential manometers. Computer-controlled acid filling stations meter electrolyte volumes with gram-level accuracy. Formation lines use IGBT-regulated charging to manage current, voltage, and bath temperature in real time, ensuring stable electrochemical activation. Before packaging, every unit undergoes 100% electrical inspection, dimensional checks, and charge retention verification, preparing the batteries for global deployment in power-critical applications. The Vietnam CRA 800 TPD graphite ore dressing plant project is a successful mineral processing project supported by Shinhai. Based on professional mineral tests, a stable and efficient flotation process was designed to improve graphite recovery and product quality. The project achieved high performance through optimized crushing, grinding, classification, and flotation stages, using a simple and economical reagent system. With strong technical support, the plant reached excellent recovery and concentrate quality, creating significant economic value. Shinhai also provided complete services, including testing, engineering design, equipment manufacturing, installation, commissioning, and worker training. This one-stop service helped the project achieve stable operation, improve productivity, and long-term operational efficiency, contributing to sustainable development and strong project performance. At the Lac des Cygnes graphite mine, the production cycle begins at the ore body, where geologists define drill patterns and blasting crews execute controlled explosions to fragment the graphite-bearing rock. Once the blast is complete, hydraulic excavators load the broken ore into haul trucks for transportation to the primary crusher. In this first reduction stage, large rock fragments are crushed to a manageable size and transferred by conveyors to the grinding circuit. During grinding, the ore is mixed with water in ball mills, producing a slurry in which graphite flakes begin to separate from the gangue. This slurry then enters the flotation circuit, the heart of graphite processing. Here, collectors and frothers are added in carefully measured drops to enhance the hydrophobicity of graphite particles. As air is introduced, graphite attaches to the bubbles and rises to the surface as a concentrated froth, while waste minerals sink. The concentrate passes through multiple cleaning stages to achieve the required carbon purity. It then flows to wet screening, where material is classified by flake size. Coarse, medium, and fine fractions are separated to meet different market specifications. Spiral separators enhance the recovery of intermediate-sized flakes using gravity and drag forces within a helical flow pattern. After classification, the graphite concentrate enters the thickening circuit, where settling tanks remove excess water and increase slurry density. The partially dewatered concentrate then moves to filtration units, typically pressure filters or vacuum belt filters, which reduce moisture content to the level required for final drying or further purification. The resulting graphite product is essential to the green economy. In lithium-ion batteries, graphite forms the single largest component of the anode, representing nearly half of the total battery mass in NMC 532 chemistries. With global energy storage accelerating, high-quality natural graphite from mines such as Lac des Îles and Okanjande in Namibia remains a critical strategic mineral, supporting the transition to cleaner technologies. Emax Inc. is a leading non-ferrous metal producer, specializing in advanced lead recycling technologies that support anthropocentric, eco-friendly energy solutions. In a global market where competition intensifies and raw material supply becomes increasingly unstable, the company provides a reliable source of high-quality recycled lead, essential for the electricity, automotive, and industrial sectors. With geopolitical conflicts concentrating primary resources in a few nations, recycled lead has emerged as a strategic alternative, and Emax Inc. plays a central role in this urban mining shift. The company secures waste lead-acid batteries through processing agreements with more than 2,800 domestic partners. These collected batteries feed its fully integrated recycling plant in Zhangxingon, established in 2011, with an annual capacity of 40,000 tons. Operations include automated crushing and separation, rotary furnace smelting, kettle refining, and cold mold casting to produce pure lead and custom alloys, consistently achieving 99.975% purity. Through continuous investment in equipment, process optimization, and high-tech environmental controls, Emax Inc. meets global specifications while minimizing emissions and waste. With expanding international supply routes and export markets, the company is positioning itself as a future-oriented leader in sustainable, eco-friendly metal production. A fully automatic grid casting machine delivers high-precision lead grid production through continuous, tightly controlled process stages. Metal is fed into a temperature-stabilized casting head, where servo-regulated molds ensure uniform grid thickness and consistent alloy composition. Automated ladles, level sensors, and mold release systems maintain steady flow and prevent defects. Cooling conveyors solidify each grid under controlled airflow, minimizing internal stress and improving mechanical strength. Inline trimming, flash removal, and optical inspection verify dimensional accuracy before stacking. The integrated automation allows high throughput, stable quality, and improved safety by minimizing operator exposure to molten metal. Sunlight Recycling applies a holistic, fully integrated approach to lead-acid battery recycling, combining high-efficiency material recovery with advanced environmental controls. The process begins with the reception and secure storage of used batteries, supporting a throughput of up to 10 tons per hour. Batteries are mechanically crushed, and materials are separated into polypropylene, lead-bearing fractions, and electrolyte. Polypropylene is recovered at high purity, while the electrolyte undergoes 2 desulfurization stages, producing industrial-grade anhydrous sodium sulfate through controlled neutralization. Lead paste, plate grids, poles, and auxiliary additives such as anthracite, iron, and sodium carbonate are prepared as furnace feedstock. In the casting furnace operating at approximately 1000 degrees C, metallic lead is liberated, forming a molten phase ready for subsequent refining. The refining line upgrades recovered lead into ultra-high purity ingots, achieving 99.99% pure lead and tailored lead alloys for industrial applications. The facility's annual recycling capacity reaches 25,000 tons of used batteries, yielding 500 tons of pure recycled lead, with infrastructure designed for future expansion. Continuous process monitoring, strict quality assurance, and an innovative super desulfurization system ensure high material efficiency, reduced emissions, and enhanced worker health and safety throughout the production cycle. Eduardo's role centers on precise paste preparation, a critical step in battery plate manufacturing. He manages controlled mixing ratios, monitors material viscosity, and ensures uniform lead oxide distribution for optimal electrochemical performance. As a relief operator, he supports continuous production, upholds safety protocols, and maintains equipment readiness, demonstrating consistent technical discipline built over 27 years of operational experience. Synthetic anode graphite at Vianode is produced through a tightly controlled sequence engineered for battery-grade purity. Petroleum coke is first crushed, dried, and demagnetized before precision milling generates the target particle size and morphology. Impact milling further increases surface area for lithium-ion intercalation. Subsequent shaping rounds particle edges to improve packing density. In the agglomeration stage, pitch binds milled carbon into uniform granules, optimized for high-rate performance. The material then undergoes graphitization at approximately 3000 degrees C in closed, high-efficiency furnaces that transform amorphous carbon into a crystalline layered structure. Final coating with pitch enhances fast charge behavior, and rigorous sieving plus magnetic removal ensure ultra-clean, automotive-grade anode material. Inside the Warrenburg facility, the Odyssey dual-purpose battery is built with one mission in mind: deliver uncompromising power. At the heart of that performance is TPPL, thin plate pure lead technology, made possible by using 99.99% pure virgin lead sourced from North America. This ultra-clean chemistry allows engineers to form exceptionally thin plates, dramatically increasing surface area and unlocking both massive cold cranking output and true deep cycle durability, with up to 400 cycles at 80% depth of discharge. The process begins with molten lead held at 750 degrees F, continuously fed into the chill casting line. Here, a refrigerated drum flashes the metal into a flawless 1 mm strip, its thickness monitored by laser with micron-level precision. That strip moves to high-speed perforation, punching the conductive grid pattern at nearly 1000 strokes per minute. Each plate is then pasted with carefully milled lead oxide, its weight monitored plate by plate, so only perfectly balanced components continue forward. In sub-assembly, positive and negative plates are stacked with AGM separators, compressed into Odyssey's impact-resistant case, and connected through oversized intercell bridges cast from pure lead. These heavy cross-section connectors route power over the cell walls, not through them, ensuring unmatched conductivity and higher energy density than spiral cell designs. After robotic welds, epoxy-bonded sealing, precision acid filling, and a controlled formation charge, every battery faces a 400-amp high-rate discharge test. Only units meeting full specification move to shipping. Engineered plate by plate, weld by weld, the Odyssey battery is built for the demands of today's most advanced vehicles, where reliability isn't optional and performance is non-negotiable. Across global industries, K-Star batteries deliver dependable power, and that reliability begins deep inside their advanced lead-acid production line. The journey starts with plate manufacturing, the backbone of every VRLA battery. Raw lead is converted into high-purity oxide through controlled ball milling, blended with water, and mixed into an optimized paste. Automated pasting machines apply this material to precision-cut grids before the plates move through curing, drying, trimming, and buffing, each step monitored by sensors that safeguard consistency, energy efficiency, and environmental performance. Once the plates reach assembly, the process shifts into a fully synchronized rhythm. Positive and negative plates are stacked, cast-on straps are formed, and terminals are welded with robotic accuracy. K-Star operates 5 automated assembly lines, capable of producing more than 6 million small VRLA batteries and over 2 million medium and large units annually. Every unit benefits from automatic strap casting, lead sealing, terminal sealing, and continuous quality detection. Formation and packing complete the build. Batteries undergo vacuum quantitative acid filling, IGBT-controlled formation cycles, and temperature-regulated water bath conditioning. Finally, each unit passes through automated labeling and 100% inspection, ensuring safe installation, secure transport, and long, reliable service life. Modern VRLA battery manufacturing involves 3 core engineering stages: plate production, battery assembly, and formation and packing. Plate production is the foundation, beginning with lead melting, alloying, and continuous grid casting. Cold cutting systems shape the grids to precise tolerances. Ball mill oxide production generates high surface area lead oxide, which is blended with water, fibers, and chemical additives in controlled shear paste mixers. This paste is applied to the grids and sent through automated curing chambers where humidity, temperature gradients, and airflow are regulated to stabilize the lead oxide structure. Finished plates are then dried, cut, and surface buffed for uniformity. During assembly, positive and negative plates are interleaved with AGM separators and stacked under strict compression control. Automated strap casting links the plate groups, while robotic sealing systems weld terminals, apply pole sealing compounds, and verify weld penetration. High-speed assembly lines maintain dimensional accuracy and ensure correct electrolyte pathways. Formation is the most critical electrochemical stage. Batteries undergo vacuum quantitative acid filling, ensuring precise electrolyte volume. Computer-controlled IGBT power systems regulate charging profiles to convert lead oxide into active material. Circulating water baths stabilize temperature to prevent thermal runaway. Post-formation steps include washing, final drying, container finishing, automatic labeling, and 100% electrical inspection, covering capacity, internal resistance, leakage integrity, and terminal strength. This sequence ensures consistent performance, safety, and long-cycle stability for VRLA battery systems used in industrial and energy applications. The fully automated heavy truck AGM battery production line operates as a tightly synchronized sequence of precision processes, engineered to ensure structural integrity and optimal electrical performance. The workflow begins with high-accuracy punching, creating uniform vent and terminal openings. Group position adjustment systems then align plate packs with micrometer precision, before robotic cell inserting units place each group into its designated container. Cause welding forms the primary current pathways, followed by automated polarity testing to verify electrical orientation. Next, TTP welding establishes durable intercell connections, supported by inline weld quality diagnostics to detect microdefects in real time. Each cell receives anti-vibration adhesive to enhance durability under the severe dynamic loads typical of heavy-duty trucks. Heat sealing machines then fuse the battery lid to the case, forming a rigid, leak-proof structure. The line concludes with advanced airtightness testing, ensuring every AGM battery meets stringent reliability standards for high-demand commercial applications. Rolls Battery's deep-cycle lead-acid manufacturing line is engineered for durability and high charge throughput. Heavy-duty grid alloys are cast and pasted with controlled density active material to support repeated cycling in renewable energy, marine, motive power, and rail applications. After curing, plates are assembled into robust cell groups and sealed into thick wall cases designed for vibration resistance. Electrolyte filling is precisely metered, followed by MERT formation, where computer-regulated charge profiles activate the plates. Each unit undergoes performance verification, capacity checks, and full quality inspection before release. The rapid expansion of global vehicle fleets, combined with the shift toward electrification and advanced onboard electronics, imposes escalating performance demands on automotive batteries. Modern vehicles integrate start-stop systems, high-load auxiliary devices, and partial to full hybrid architectures, all requiring higher charge acceptance, deeper cycling capability, and improved thermal stability. Battery management systems must track state of charge and state of health with greater precision to prevent voltage drops affecting safety-critical modules. Evolving OEM platforms also tighten packaging constraints, necessitating batteries with optimized energy density and vibration resistance. As electrified drivetrains proliferate, the industry must deploy advanced chemistries and diagnostics to maintain reliability across increasingly complex electrical networks. The upgraded production line integrates two MAC Dynamax COS machines that deliver highly consistent strap thickness and reliable metallurgical bonding between lead plates and straps, ensuring electrical integrity for golf car batteries. A TBS engineering welding unit supported by external weld monitors verifies every weld in real time to maintain strict quality thresholds. Additional inspection stations validate heat seal strength and apply precise date coding for traceability. A new acid filling system will enhance dosing accuracy and process stability. Overall throughput is expected to rise by 25 to 33% without increasing manpower. The line supports 6-volt, 8-volt, and 12-volt battery formats, establishing a scalable platform for future capacity expansion. The newly built CS Power Battery Factory is engineered as a high-efficiency, precision-controlled manufacturing hub for advanced lead-acid and renewable energy battery systems. Automated grid casting, high-speed pasting lines, and temperature-regulated curing chambers ensure uniform plate density and stable electrochemical performance. COS and robotic welding stations deliver consistent strap bonds and low-resistance connections across all battery types. The plant incorporates sealed formation rooms with controlled charging profiles, followed by computerized inspection for voltage stability, internal resistance, and leak integrity. Integrated MES tracking allows full traceability from raw materials to finished packs, supporting scalable production for automotive, solar, and industrial energy storage applications. Underground mining below deep levels demands reinforced tunneling, high-capacity ventilation, and continuous gas-water monitoring. At the -150 meters horizon, crews advance excavation with mechanized drilling, roof bolting, and stable conveyor haulage, ensuring structural integrity, controlled strata pressure, and safe, uninterrupted coal extraction under increasing geological stress. Manufacturing polyester staple fibers from post-consumer PET bottles begins in the PET bottle washing unit, where incoming waste bottles are manually and automatically sorted on dedicated conveyors. Labels, caps, and contaminants are removed before bottles enter high-pressure washing, producing clean PET flakes. These washed flakes are packed and transferred to the fiber production line. In the melting stage, PET flakes are dried and fed into extruders, where controlled heating converts them into homogeneous molten polymer. The melt is filtered and directed to the quench area, forming continuous filaments that are solidified by chilled air. The filaments move to the winding section, then through drawing and crimping systems to create the primary fiber structure. In the creel and dry sections, fibers are tensioned, heat-set, and stabilized before cutting into uniform staple lengths. Quality is verified in the PSF laboratory, and finished fibers are stored in the final product go-down. Parallel lines manufacture polyester filament yarns, such as POI and FDY. Melt extrusion forms filaments which are quenched, wound, and tested in dedicated POI labs. FDY ropes undergo precision twisting in Unit 04 before packaging. Together, these integrated units convert recycled PET into high-value textile and industrial fiber products. Clarios. Total Systems approach emphasizes how modern vehicles demand a re-engineered low-voltage power architecture. As electrification and digitalization accelerate, automakers are shifting toward zonal electrical layouts to optimize data flow, voltage distribution, and system efficiency. This evolution increases the load on low-voltage networks, requiring batteries capable of stabilizing power delivery for safety, performance, and autonomous functions. Clarios supports this transition with advanced low-voltage solutions integrated into the vehicle's broader electronics ecosystem. Their closed-loop recycling model strengthens circularity, ensuring end-of-life batteries, regardless of chemistry, are recovered and reprocessed. As vehicles become more complex and energy-intensive, a robust system-level low-voltage strategy becomes essential, positioning Clarios to help shape the next era of automotive power management. A China-led acid car battery manufacturer factory tour offers a concise 5-minute look into how modern Chinese facilities produce high-quality automotive batteries using fully automated, high-throughput technology. The process opens inside a dust-controlled lead alloy preparation hall, where molten lead is purified and blended with calcium or silver to form corrosion-resistant alloys. These alloys feed continuous casting and grid punching machines that produce thin, uniform grids with precise dimensional stability, an essential foundation for plate performance. Next, Oxide mills feed automated paste mixers, creating an active material blend tailored for fast charging and long cycle life. High-speed pasting lines apply this paste onto positive and negative grids, followed by controlled curing ovens that optimize crystal growth and mechanical strength. Cured plates move into assembly lines where robots stack them with AGM or PE separators, weld plate groups, and insert them into molded polypropylene cases. Electrolyte filling, heat sealing, and advanced tank formation systems activate the battery under monitored electrical cycles. Each unit undergoes leak checks, capacity verification, and internal resistance measurement through online testing stations. Finished batteries are laser-coated for traceability, automatically cleaned, labeled, and palletized. The tour highlights how China's modern battery factories combine automation, strict process control, and smart logistics to deliver reliable, high-performance lead-acid car batteries for global markets. Amaron Battery Manufacturing is built around a high-precision, contamination-controlled production environment designed to deliver long-life, maintenance-free automotive batteries. Using high-speed continuous casting and punching lines, these grids achieve uniform thickness and optimized grain structure, ensuring consistent electrical performance and mechanical durability under high cyclic loads. Active material production follows a tightly controlled paste mixing operation. Oxide, demineralized water, and additives are blended in automated mixers to create a highly reactive paste, which is then applied onto positive and negative grids through precision pasting machines. Next, plates are assembled into plate groups using automated strap welding systems, ensuring low-resistance intercell connections. Each battery undergoes automated case molding, heat sealing, and electrolyte filling using purified acid formulations. Amaron employs expanded metal technology, vibration-resistant separators, and robust polypropylene housings to withstand harsh climates and high engine bay temperatures. Formation charging takes place in modern tank formation lines that gradually activate the plates for optimum capacity and cycle life while minimizing energy consumption. Once formation is complete, batteries are sealed, cleaned, and subjected to rigorous quality checks, including high-rate discharge testing, leak detection, and internal resistance measurement. Packed and palletized through automated logistics systems, Amaron batteries are shipped globally, recognized for their high cranking power, extended lifespan, and proven reliability in demanding automotive and industrial environments. The DKM plastic battery case molding line is engineered for fast and stable production, delivering a consistent 40-second cycle time for polypropylene battery cases size 277 x 174.5 x 165 mm. A DKM 450 servo motor injection molding machine provides precise control of pressure, injection speed, and cooling, ensuring uniform wall thickness and accurate dimensions. The system integrates a top-entry industrial robot for rapid product removal, reducing the risk of deformation during ejection and improving repeatability. A modern production line for recycled polyester staple fiber begins with post-consumer PET collection, sorting, and mechanical cleaning, followed by high-temperature shredding to create uniform flake feedstock. These flakes are conveyed into continuous decontamination reactors, where vacuum, heat, and inert gas purging remove residual polymers, additives, and moisture. The purified flakes enter an extrusion system equipped with twin-screw compounding, allowing precise melt filtration through multi-layer screens to ensure stability of intrinsic viscosity. The molten polymer stream is delivered to spinnerets, where dozens to hundreds of capillaries extrude filaments simultaneously. Quenching towers use controlled laminar airflow to solidify the filaments, while oil application units apply spin finishes that optimize cohesion and downstream processability. Filaments then move through high-speed drawing frames, where thermal stretching aligns molecular chains and improves tensile properties. After drawing, the tow is passed through crimping machines that introduce three-dimensional waviness essential for bulk and blend behavior. The crimped tow enters forced air dryers to remove residual moisture before being precision cut into staple lengths, typically ranging from 32 mm to 102 mm. Automated baling systems compress and strap the finished fibers for downstream use. Comparable processes are applied when producing viscose (PLA) and soybean protein staple fibers, with adjustments in dissolution, spinning medium, and solidification chemistry tailored to each material's rheology and performance requirements.